Good morning, everyone. Thank you very much for joining us today for the Innovation for Cool Earth Forum, the 10th annual meeting hosted by the Ministry of Economy, Trade and Industry and New Energy and Industrial Technology Development Organization. Now we would like to start the session. My name is Yuri Tachibana, and I'll be the MC for this session. Now let us begin ICEF Roadmap Project, Artificial Intelligence and Climate Mitigation. Now I would like to introduce Mr. David Sandalo to moderate the session. Mr. David Sandalo is ICEF Steering Committee, Inaugural Fellow, Center on Global Energy Policy, Columbia University, Co-Director, Energy and Environment Concentration, School of International and Public Affairs, Columbia University. Mr. Sandalo, if you please.
Thank you, Yuri, and thank you to the entire team here at ICEF, really just organizing an amazing conference. I'm so impressed once again at how you've pulled together such a compelling agenda. Thanks to everybody who's working behind the scenes. Thanks to our chair, Nobuo Tanaka. We're honored that you join us here for this session, Tanaka-san. And I'm very excited to be releasing today a draft roadmap on artificial intelligence and climate change mitigation. This draft is going to be open for comment throughout the month of October, and then we'll finalize it and publish the final one in December. And I'm joined both here in the room and around the world by some of the team of co-authors who you see on this front page here. We've had a tremendous team of co-authors working on this roadmap for the past 6 months. So here on the stage, I'm joined by Alp Küçükkelbir, who is chief scientist at Faro Labs and a professor of artificial intelligence at Columbia Engineering School. He teaches that topic. And by Trisha Negrani, who is just been a Schwarzman Scholar at Tsinghua University and is the co-founder of a company called Haiku that works in this space. And then on the screen, we see, starting from the top left, Fan Jiwan. Fan is at Columbia Engineering School. Elena Mendez-Leal, who is at the School of International Public Affairs at Columbia and the Center for Climate Systems Research. Colin McCormick, who teaches artificial intelligence at Georgetown University and is Chief Innovation Officer at Carbon Direct. And Julio Friedman, who is the Chief Scientist at Carbon Direct. Really just an extraordinary team, thrilled to have the opportunity to work with all these people. And we're going to spend the next half hour or so telling you about what we've done, and then have a dialogue and take your questions. So this is actually the 12th ICEF roadmap. And huge thanks to Nito and to Mehdi for their support through the last 8 years in developing these ICEF roadmaps. It's particularly been an honor, a thrill for me to work with Colin McCormick and Julio Friedman, who you see on the screen, working on so many of these ICEF roadmaps over the years. And today we're releasing this one on artificial intelligence for climate change mitigation. And just to start, this is the topic that our roadmap addresses. How can AI help reduce emissions of greenhouse gases? This is a big topic. Artificial intelligence is a very hot topic today. In November 2022, ChatGPT was released by OpenAI. It quickly became the most rapidly adopted product in the history of humanity. By January 2023, there were more than 150 million users of ChatGPT. And today, there are about 1.5 billion visits to the ChatGPT website every month. And as a result of that, the topic of artificial intelligence has gotten extraordinary attention. But artificial intelligence is more than ChatGPT. It's more than large language models, as we'll discuss here. But we decided to use the occasion of all this attention that AI is getting to ask the question, how can AI reduce emissions of greenhouse gases, help us get to net zero, which has been a theme of this conference. Here are 2 questions that we don't ask in this roadmap, just to frame what the dialogue is about. We didn't look at how AI can help adapt to climate change. I think AI tools can do a lot in helping to adapt to climate change, but that's another roadmap. And we also didn't look at the bigger question of, on balance, will AI help or hinder the fight against climate change? That's a big and really important question. But our roadmap is focused on how do we help make sure that AI does the most good it can in fighting climate change. Here's our table of contents. 3 big parts to the roadmap. First, some background. All these roadmaps, we try to write them both for a generalist audience and for a specialist audience. And we have introductory material in this roadmap, just a background in AI for people who may not be familiar with it, and background on climate change science and climate change for people who may not be familiar with that topic. Then we discuss 6 high potential opportunities for using AI to fight climate change to reduce greenhouse gas emissions, and then some cross-cutting topics, barriers, risks, policies, and then we end with findings and recommendations. And we start with background, and from here, we're going to go, and all 7 of us, I guess, are going to talk. It's a bit of an experiment. We'll see it's a lot of people to be presenting. You're going to see a lot of people jumping in and out talking, and then at the end, we'll take some questions. So we'll start with an introduction to AI, and Professor Kucha-Kelbir wrote this section. He'll talk about that.
Yeah, thank you so much, David. It's really a pleasure to be here, and it's a wonderful avenue to be having these conversations. So thank you once again to Takana-san for the invitation and for sponsoring such a wonderful project. So you have no doubt heard of artificial intelligence. You likely have also encountered the term machine learning and might be wondering at a high level, how does artificial intelligence and machine learning relate to the 60, 70 plus years that we've had kind of computation be a major component of our lives. So there are various technical definitions of artificial intelligence that we could have adopted for this report. Instead, we preferred one that really captures what we think is the essence of what AI can actually do in mitigating climate change as well as transforming various aspects of our lives. So we define artificial intelligence as the science of making computers perform complex tasks. Oftentimes, these tasks are associated with human intelligence, therefore kind of giving the name to AI in a way that connects to what we think of as human intelligence. Now, AI actually relies on a subset of computer science that is called machine learning, again, a term that I'm sure you have been exposed to, where we look at machine learning as the subset of computer science that focuses on detecting patterns from large data sets. In this way, you will see throughout the report that we think of AI as relying on machine learning, and wherever relevant, we will distinguish between a topic that is leveraging specifically machine learning or one that is using AI and leaning on machine learning to accomplish those goals. So AI differs from traditional software in the way of, instead of relying on explicit programming, AI relies on historical data simulation to so-called train models and learn patterns. And the picture that you see on the right-hand side summarizes that relationship. There are 3 components to AI: data, a model, and computation. And if we switch to the next slide, I'll be able to dive a little bit deeper into these. So AI and machine learning relies on these 3 main components. Let's describe what they are. Data are observations that pertain to a particular problem we are looking to analyze. A good example in the climate sciences would be historical weather patterns. A topic that we will dive into in depth in the report is the importance of availability of data and accessibility to data, and we'll specify how these 2 things are different and how they have an interplay in terms of enabling AI applications. Once you have access to data, next comes the model. The model describes the objective of what the AI system is attempting to achieve. It also describes patterns that lie in data. In the weather example that we have here, this would be a description of what types of patterns, whether it is meteorological patterns, weather systems that we expect to get from that data. The model, combined with computation, which is a set of mathematical and statistical algorithms, computer programs, and computer hardware to run these programs, trains the model to detect these patterns from data using machine learning and achieve its objectives. So we'll touch upon data, model, and computation in all of the 6 areas that we will be describing in this presentation.
Thanks, Alp.
Hello. It is nice to be here today. As we have been hearing for the last day, everything about climate change and all of its effects that we have been experiencing today. But I would like to highlight a few things regarding the climate crisis in specific that we have. I would like to highlight the picture we see at the top right. For the last 800,000 years, today is the day we have the most or the highest level of atmospheric concentrations of heat-trapping gases, like carbon dioxide, methane, and other gases. Similarly, for the last 150 years, since 1880, we have seen that the global average temperature increasing by 1.1 degrees Celsius. And I think we've started to experience that heat a little bit. This summer, from June to August 2023, was the warmest summer ever recorded. July was the warmest month, and July 6th was the warmest day. In fact, I was actually reading just today in the morning in the news that September is also considered the warmest September ever recorded, including here in Japan, and in the UK and New Zealand as well, confirmed. But this is just the tip of the iceberg, and I think that's also melting. So a few other things I would like to also highlight are climate records that we will continue seeing and extreme climate events that scientists have been predicting. And I think someone rightfully said yesterday, we're going from warning to warming to boiling. Some of those examples could be like the wildfire we heard about Hawaii just a few weeks ago, or the floods in Pakistan last year that affected, I think, more than 33 million individuals. So taking this as the last point, which I would love for you to take with you, is if we look at all the policies we have today in place or partially being implemented, it is expected that the global average temperature will increase by 2.9 degrees Celsius by 2100. This is well above the thresholds we heard or adopted at the Paris Agreement in 2015. So the point I would like you to take on the climate crisis today is we're not on the path to achieve our climate-related goals. Thank you.
Thanks, Trishna. And I just want to say this, one of the things I love about the ICEF conference, this is a very humbling experience. We are briefing about the science of climate change. And in the audience, we have Professor Ho-Sung Lee, the immediate past chair of the Intergovernmental Panel on Climate Change, and we're honored that you're here listening to us. So thank you, Professor. And maybe we'll find a way to bring you into the conversation after this. And we can ask you whether we got it right. This chapter cites extensively, of course, from the last assessment report of the IPCC. And our next, Julio can take it away on this.
Excellent. So next slide, please. So against this backdrop of urgency, you may be surprised to learn that AI has already made substantial contributions in climate science. And you'll hear from others that it's making contributions in other arenas. One good example of that is we've just improved the performance of climate models. AI has already helped us do model intercomparisons. It's already helped us to provide a complement to sort of the physics-based models. It's reduced the computational intensity, a lot of the way that we analyze or work the models. And importantly, it's helped us identify potential biases in our models. Because models have these kind of biases in them, AI, if you train it properly, if you use the right objective function, can help you identify those, which provides progress. Completely separate thing, we have already identified new climate processes and feedbacks. I have to say that's not all good news, actually. We've learned from that, actually, we may have less time or more difficulty than we thought. Just one example of this, we've learned that precipitation in the Midwest affects the salinity in the Atlantic, or learned something about the way that aerosols and clouds behave together. It has also provided advance warning for some extreme weather events using what's described as nowcasting, running these models in real time and trying to understand extreme events. Completely different way they've helped is to attribution for extreme events. We see these extreme events like Trishna was describing, and the question is, well, is this really caused on us? In some cases, you can show not so much. In many cases, it is clear what the fingerprint of human attribution is. For example, the recent flooding in Europe, tropical cyclone intensity, the growing occurrence of extreme frost events, all of these, the AI have revealed to be human-induced. Last but not least, we have seen additional climate drivers, which were not anticipated from that. A recent study, for example, on ship tracks and the clouds that are made by ships because of dirty fuels, we've learned actually how to quantify the attributes associated with that, and more importantly, as we clean the fuels, how that affects the formation of aerosols and affects the formation and affects the albedo of the Earth. All of these are recent, but again, the power of the computations, the ability of these models show us something that we did not understand before.
Thank you, Julio. And then the next section of our roadmap talks about high potential opportunities. We have 6 in the roadmap, and we'll just run through them to give you a sense of what we discuss, starting with the section on greenhouse gas emissions monitoring, for which Colin was one of the key co-authors.
Thanks, David. One of the important emerging areas where AI will help us with climate mitigation is improving our ability to monitor greenhouse gas emissions. Now, of course, we have existing tools like the Ibuki 2 satellite you see there that can measure CO2 concentrations in the atmosphere, but that's different from delivering the ability to do high spatial and high time resolution attribution of emission sources. AI is helping us do that by analyzing vast amounts of data from multiple sources, including remote sensing and in situ sensors. There's 2 particular areas we highlight in the report. One of those is improving methane emissions monitoring, an emerging area that we had badly underestimated in the past. AI can help us process data from methane sensors at scale, combine input from multiple satellites, and integrate satellite information with other data. AI can also help us better understand CO2 emissions. That includes better surveying vegetation for above ground biomass, and also point source emissions from industrial facilities such as power plants. We'll go to the next slide. A set of barriers, of course, exist to better use of this technology. One of those very broadly is a lack of AI literacy in the general population, in governments, and in some parts of the private sector. There is potential for conflicting data when different AI algorithms are used, and there need to be methods to resolve that. There may be sovereignty concerns with using remote sensing and AI to monitor emissions in other countries. And of course, there's financial models that need to be better worked out to support both the hardware and software of these integrated systems. We identified several measures to help address these barriers. Those certainly include promoting AI literacy, establishing mechanisms that can validate the AI-enabled GHG emissions data and ensure that it's harmonized, potentially setting up one or more global owners of the AI-enabled GHG emissions data coming from multiple sources, and of course, elevating AI for climate in international dialogue and also in climate negotiations.
Thanks, Colin. Thanks, Colin. And Fan wrote the section on the power grid. Fan, floor is yours.
Thank you so much, David, and thank you everyone for inviting me here. So another sector that artificial intelligence AI can not only be a very big influence, but also become an essential part of its transition is the power grid infrastructure. So there have been a widely studied topic about how AI can make the power grid transition to be cheaper, faster, and smoother. One of the most widely explored topics is AI can help us with the predictions. For example, it can help us with a short-term prediction in terms of solar and wind generation for tomorrow, or demand, or in terms of hydropowers. Or it can do long-term projections in terms of scenario generations. AI can combine the socioeconomic data such as GDP, developments, electrification potentials, and etc., and give us a more clear pathway towards the future. AI can also help us to solve the existing problems more efficiently or provide much more better solutions, such as replacing or partially helping the optimization problems that we're using today to develop energy system models or to solve, for example, transmission optimal power flow questions. And aside from AI of helping us at a specific sector, AI can also help us with combining all these different parts together and come up with a systematic and integrated plan of operating them in a systematic way. So from these examples, we can see that AI has the potential to cover a transition and help the transition to be cheaper, faster, and smoother in almost all the components, from generation of renewables, wind and solar, to the delivery of the electrons in the transmission and distribution grid. And also it can help us with the energy end uses such as the Internet of Things, EVs, heat pumps, and also help us to maintain the grid stability such as energy storage. But in order to make a successful impact, there are some barriers we have to overcome. One of the most important one is there are a lot of innovations trajectories about how to develop a better AI model, but there are not a well-developed models that's suitable for commercial deployments. And also, we're also lacking trained personnel for AI literacy. It does not only means that we need better research, we need better developers for AI algorithms. It also means we need AI literate policymakers, users, and maintenance people to help construct a more stable environment for AI penetration. And also, when we're using AI, inevitably, we're exposing a lot of data to the artificial intelligence. And sometimes in order to make the predictions, it has to be real-time operation data. And that could potentially create security and safety risks, and we actually value our system, power system security in a very high grade. So in order for AI to make a successful and good impact, these barriers and risks has to be answered in the first place. And from here, I can take to the next page, talking about manufacturing.
Perfect, yes. So manufacturing is responsible for about 1/3 of global emissions, and decarbonizing manufacturing is a particularly hard topic, largely because of the physical and chemical requirements and constraints that go into the manufacturing of things like steel, cement, and chemicals. Now, these industries require long-term investment to decarbonize, such as hardware changes into how these materials are produced in the first place, different chemical reactions, various innovative approaches to manufacturing these materials, carbon capture, utilization, so on and so forth. Process changes that will also take a certain amount of time, switching from using raw ingredients that are mined from the earth to adopting to increasing amounts of recycled feedstock, and switching to electrification in production systems that are reliant on fossil fuels at the moment. Now, our position here is that while these investments are necessary and they are already happening today, AI can provide a complementary benefit that can work with existing hardware and existing facilities. And the image on the right-hand side captures one of a variety of themes in which AI can actually have a significant impact in manufacturing. Here on the top side, we have an example of a manufacturing plant that is operating today without AI, using virgin feedstock. These are raw materials with perhaps some recycled feedstock, and unable to work with the variability that is introduced by the recycled feedstock. The result of this is the manufacturing plant incorporates a certain amount of over-design, you can think of these as buffers, and produces reliable products, that's good, but with excess CO2 and additional waste that could be avoided. The picture below shows a plant operating with AI optimization being able to adapt to mostly, if not only, recycled feedstock and still producing reliable products with a net CO2e reduction. If I might request the next slide. There are other ways in which AI can have an impact in manufacturing. One is in decarbonizing the process of making things, the example from the previous slide, such as enabling an increased recycled or circular feedstock. In decarbonizing supply chains by optimizing manufacturing schedules. implementing dematerialization strategies, which were highlighted in the past two IPCC assessment reports. The approaches here would be to design stronger or lighter materials that have a much more positive life cycle analysis prospect, and decarbonizing the maintenance of manufacturing equipment, such as forecasting various process conditions and making sure that we take care of our factory equipment in the most optimal way. Like all of the sectors that we are describing in this report, adopting AI in manufacturing faces a variety of barriers and risks. Two that I'd like to highlight here is the lack of manufacturer incentive to decarbonize, and additional safety risks, similar to the power grid that Fan mentioned, of adopting AI-based workflows in live operations, real-time operations.
Another important area is in materials innovation. So we know that novel high-performance materials are crucial for many areas of decarbonizing the economy. That includes examples like high-performance photovoltaics, high-strength magnets, battery cathode materials, and carbon capture sorbents. Historically, novel materials have been discovered somewhat by accident or alternatively by exhaustive, expensive, slow experimentation campaigns. Thomas Edison's discovery of a filament for light bulbs is an example where thousands of potential materials were tested before identifying the one with the right performance. In recent decades, it has become possible for materials scientists to shift into a computational paradigm where fundamental algorithms and numerical approaches have been able to predict the macroscopic properties of novel materials from their microstructure and their atomic composition, even in cases where they haven't been actually materially synthesized. However, that is very computationally intensive and very slow, and this is an area in which AI can dramatically increase the capacity to use computational materials science. So we'll go to the next slide. Some examples of that include rapidly screening millions of potential materials for important properties. Those may be materials that have been synthesized or may simply exist in theoretical databases. AI can help accelerate materials experiments to test sample materials that have been synthesized and interpret experimental data rapidly. Natural language processing can be used to synthesize published materials literature, which can number in the tens of thousands of research papers for single subcategories of materials. And when we move into generative AI models, there is great potential there to generate new concepts for novel materials that have not really been a part of computational material science to date. Of course, there are many challenges here. Accelerating the use of AI in materials innovation needs better harmonization of existing materials databases. It would be extremely helpful to stand up an increased number of semi-automated, high-throughput materials testing facilities, some of which could be operated remotely to broaden access to the global material science community. And better focus on the embedded or the manufacturing emissions of these novel materials, and including a life cycle assessment of both the manufacturing and use phase of novel materials in these AI algorithms.
Everyone, for food systems are critical for sustaining livelihoods and food and nutrition security globally. And as we know, climate change has exacerbated food production and supply, but food systems in themselves are a significant emission contributor. Land use, agriculture production, supply chains, and ultimately consumption and waste are estimated to be responsible for over 30% of global greenhouse gas emissions. Now, when we consider how applications for artificial intelligence can reduce food systems emissions, there's a multitude of opportunities in this space and many that are already being implemented. From renewable agriculture, one of our examples on this slide includes using biophysical input data for precision farm and fertilizer management to reduce emissions in that area, and then also enhancing soil carbon sequestration, potential optimization of energy use and waste in food supply chains, and even accelerating the development of alternative proteins, which tend to have a lower footprint compared to other more traditional proteins. Now, ultimately, striking a balance between food emission reduction objectives and other food security imperatives is both a key design constraint and a significant obstacle. But as we need to, or we're striving to achieve both of these goals, AI is a potential avenue to explore and is not necessarily the solution, but as a complementary tool to the efforts that are already being put in place. Now, as some of these challenges have been mentioned, but I think ones that are particular for food systems are costs in development, infrastructure, and use, data quality and availability to even have a functioning AI model, and potential misuse and even buy-in. And a few considerations when we try and apply and integrate AI into lowering food system emissions is developing a wide stakeholder approach for AI applications, and this can include expanding and scaling existing technologies and integrating them into more traditional models, and also investing in artificial intelligence that is explicitly tailored for different food systems processes. And I will pass it along there.
And the final sector that we discussed in this roadmap for the application of AI is road transport, which is 18% of global energy-related CO2 emissions. And there's significant potential for AI to contribute to the reduction of emissions in this sector. The areas that we discussed include batteries and novel development development of novel chemistries using AI tools, the same with sustainable biofuels. The optimization tools in AI can be very helpful for developing intelligent transportation systems and in evaluating potential shifts towards modes of transport that emit less carbon, and modal shifts, and figuring out how to incentivize people to use mass transit, what patterns work best, those types of issues. As in other areas, the barriers include a lack of data, lack of uniform standards, and a shortage of personnel. And there are a number of risks, including bias and invasions of privacy. And here, I think, strikingly, probably the leading application of AI in the road transport sector today is in the development of autonomous vehicles. And it is not at all clear that the development of autonomous vehicles will be a good thing for greenhouse gas emissions. It may well be a very bad thing for greenhouse gas emissions by lowering the incentives to driving, increasing vehicle kilometers traveled, and as a result, emissions. So we don't dive into this in detail in the chapter, but there's a real potential, there's a real risk in the application of AI in that area, in the road transport sector. So we've just been through 6 different applications of AI in 6 different sectors for cutting greenhouse gas emissions, in greenhouse gas emissions monitoring, in the power sector, in materials innovation, in manufacturing, in the food sector, in road transport. I think we could have done 6 more. I mean, AI is a broadly applicable tool that's going to transform lots of sectors in the years ahead. But we chose these 6 because we think they're particularly interesting and important. And then having done that, we look at cross-cutting issues in this roadmap. And the first cross-cutting set of issues we look at are barriers.
Yes, so you've heard us mention in the different kind of application areas very specific barriers. If we kind of take a step back and just analyze patterns that we saw across all of these different topics, we identified 5 different barriers that impede the development, adoption, and use of AI in these specific areas. And these break down as data, people, computation, cost, and institutions. Very briefly, and we can have a discussion later on if we'd like, data is about having a trained AI workforce as well as domain experts in each of the specific areas such that there can be a healthy collaboration between experts in these specific areas and those who are trained to develop, build, and deploy AI models. that was the people, apologies. Starting on data, of course, is the data accessibility and data availability questions. So data that is available is measured and well digitized to be ideally powering AI applications. Data that is accessible can be ideally accessed by a wide group of people, either for free or at cost with liberal licensing permissioning, allowing various AI systems to be built. Now, with data and people who can leverage that data comes the question of how we are going to actually build these AI systems, what types of computers are we going to use, how are we going to actually train the models. That's where computation becomes an important thing to consider, whether it is on hardware that you have access to or cloud computation. And especially in the cloud computation setting, we have the question of cost. Having access to computational hardware, paying for access for that hardware, and enabling the training and deployment of AI algorithms comes with a considerable cost. And institutions combine all of these topics in terms of supporting and potentially impeding the adoption of AI in these application areas.
Thanks, Alp. And we're going to speed up a little bit because I see we have about 21 minutes left, and we want to leave some time for the audience to come in. But let me turn it to Trisha to talk about some risks.
Regarding risks, the way we saw it, and as Alp mentioned, barriers are what is impeding us from adopting or deploying AI. But once we have done that, what are the risks that we can face? There are 4 that I would like to very quickly highlight. Biases. It could come from maybe cultural biases of the researcher or developer working on the AI model. It could be historically unavailable data, maybe for certain countries or certain groups. It could also mean invasions of privacy. And this is mainly because AI models require large amounts of data. It could be proprietary, sensitive, or even personal data. So some of the risks that we more or less face are, what if there is unauthorized surveillance or breaches of data? And sometimes even being able to identify personal information if we merge different data sets. Another one is security threats. I personally view them as 2 sets. One is the same security risks that we see with IT infrastructure. Where is the data being processed? How is it being processed? And more importantly, maybe who has access to that data? The second one is more AI specific, and that's specifically more important when it's looking at real-time data entering into the AI models, where deployment is necessary or even being able to adapt and maintain those AI models as it's taking in real-time data. And the last one I want to focus on are safety issues. But these are prone for certain applications that we saw in the prior ones: agriculture, manufacturing, chemicals, or even energy. And we have covered some of those. One very quick example I can give is, what if there's an AI model that's optimizing, let's say, for grid operations? It's optimizing for those, but it's maybe not looking at the safety conditions of the workers in those workplaces. There's a last one that we want to focus on, and David will take it on, which is the increasing use of greenhouse gas emissions from using AI models.
We did a deep dive on this topic, looking at will computing operations from AI significantly increase greenhouse gas emissions? And here are our conclusions. First, in many ways, most important, the data here are very poor. We need better data collection. We need better assessment methodologies in order to really get a hold on this issue. But currently, based upon the available data, we think the emissions are modest from computing operations for AI, significantly less than 1% of the global total, looking at the existing literature. But it raises the question, what's going to happen in the future? Because AI is transforming everything in the years ahead. Is that going to lead to massive increases in greenhouse gas emissions? And there's significant concern about that. And our conclusion is the uncertainty range is enormous on this. And there are a number of different possible futures. And in some scenarios, it is possible that emissions from AI could actually go down in the years ahead. In other scenarios, it's possible that they could skyrocket. And you see here on the slide the factors that are relevant. One factor that's relevant is how much does AI increase in the years ahead, and that's probably going to be pretty significant. But then at the same time, how much does the energy efficiency of AI equipment increase or improve? How about the processes used to manufacture AI equipment? Both of those have been improving dramatically in recent years. Another area where there's been significant improvement is the optimization techniques in AI models. And so if all those improve at a faster rate than the demand for AI increases, that we may well not have significant increasing energy use from AI. And then very significantly, how much zero carbon electricity do we use in data centers and other applications for AI? And actually the hyperscalers, who are the major operators of data centers, are the world's largest purchasers of renewable energy right now. So a lot of uncertainty in this area, but a very important topic. We have a chapter on policy looking at policies that promote the use of AI and policies that manage risks related to the use of AI. I'm going to skip over this for now, just given time constraints. And we are going to close on findings and recommendations. And I'll turn it over to Julio to talk about our findings.
Excellent. So first is, it's already helping. Artificial intelligence is contributing to climate change mitigation, and it has the potential to make significant contributions in the year ahead. The converse is also true. AI is not a panacea when it comes to climate change. It doesn't deploy hardware, it doesn't move molecules. There's limits to what you can expect from it. Critical finding, right now the lack of trained personnel and the lack of high quality data are the critical barriers. Again, the lack of trained personnel, the lack of high quality data are the critical barriers to getting this deployed and deployed well. Because of its potential, significant resources will be required for this to make a dent. If we really want AI to contribute substantially to climate mitigation, we're going to have to put money and staff and resources into it. Next slide, please. There are substantial risks from AI. These include the biases which were described earlier, the potential concerns about privacy, security issues, etc. These risks exist when you use AI for climate mitigation, in many cases, as they do for AI use generally. As David just attested, the greenhouse gas emissions from computing infrastructure for AI appear modest, significantly less than 1% of the global total. Again, better data would help with this, because, last point, the amount of future greenhouse gas emissions from AI is highly uncertain. We need to keep an eye on that, and we need to improve the data that we gather and analyze in order to avoid a bad outcome. This takes us next to recommendations.
So wrapping up with our recommendations, I'll run through them. First, AI tools should be integrated into many aspects of climate change mitigation. AI is a very powerful tool, and in every aspect of climate change mitigation, there should be real evaluation consideration of how AI can help. AI skills development is a high priority. Educational institutions at all levels should offer courses relevant to this. Government agencies, businesses, civil society should regularly review the capabilities of their staffs with respect to AI. Standardization of data is a very important topic for AI, and governments can play a role. And then we recommend that all government agencies with responsibility for climate change should create an AI office. A lot to say about electric utilities and their role here. They're very important, obviously, with respect to the power sector use of artificial intelligence. And in some places, electric utilities are not incentivized to deploy artificial intelligence. They need to be, with regulated return for investments and regulatory structures that provide the incentives for deployment of AI. Governments should launch international platforms in places like the Clean Energy Ministerial and other international institutions to support cooperative work for AI and climate change mitigation. And then governments should work to minimize greenhouse gas emissions from AI's computing infrastructure. We talked about the wide range of uncertainty. It's very important that governments pay attention to this issue and put policies in place to make sure that the greenhouse gas emissions from computing operations don't significantly increase. And then avoiding unfair bias should be a core high priority principle as we develop AI tools for climate change mitigation. So thank you for listening. This roadmap is open for comment. It is going to be on the ICEF website this afternoon. Please send comments to ICEF2023roadmap@gmail.com. This will be up on the website, but ICEF2023roadmap@gmail.com. We're collecting comments during the month of October. We'll finalize the roadmap during the month of November and release it at COP28 at the Japan Pavilion. And once again, huge thanks to NATO, huge thanks to Mehdi for their support of this, and personally, huge thanks to these incredible co-authors who you've just heard talking. It's really been, it's a remarkable group of talented people. It's been my honor to work with them. And with that, I'll just throw it open for questions, see if anyone in the audience has any thoughts or comments on this topic. Thank you. For those on the screen, we are getting applause in the room. So I don't know if you could hear that, but we appreciate that. Thank you very much. I see, yep, a question back there. Please identify yourself.
Yeah, so my name is Chris, and I'm with the Trade and Investment Office for British Columbia, Canada, where we have a lot of AI companies doing interesting things in this space. I'm not a policy person, but I nevertheless try to stay on board with sort of the latest developments, so this has been very helpful. I just want to thank all the speakers. I guess this question relates to sort of bias and risk. You know, there's, across the political divide, we might associate sort of climate change denial, climate change belief, and sort of there's a bit of a political divide there. How does the bias factor into sort of, you know, public perception of the risk of sort of the potential for, let's say, bias in, bias out in terms of what the models are trying to predict and what they are actually predicting and the sort of results that are generated there? And is there any sort of bipartisan, cross-political divide, organizations, events, what have you, sort of efforts to put the public's mind at ease that this is not actually a political issue. This is, this is data. These are models that are making high, quality predictions. And yeah, I'm just kind of curious to know, because you're sort of alluding to it in your recommendations that this is what we should do. But I'm just sort of curious about current efforts like, standardization, much like the ISO standards might work in manufacturing. Is there something that might put the public's mind at risk? Or perhaps in manufacturing, put employees' minds at risk if they're handing the keys over to an AI system? What are some sort of the efforts to, abate this kind of, these potential issues?
A very interesting question, and there's a lot in that. I'll just start and then turn it over to anybody who wants to talk about it first. One very important issue that is kind of misinformation related to AI and whether AI has the ability to generate misinformation kind of on steroids. That's not something we looked at in this roadmap. In this roadmap, we look at how does one use AI to improve performance on climate change mitigation. So that's one thought. Second, there is an interesting question about the large language models and how they perform. I think if there's a lot of misinformation, in their training data sets and other information, and for that maybe I'll turn over to Alp or others.
Perhaps Julio.
And I see Julio's raising his hand. So Julio, take it away.
So to speak directly to your point, I think that this is very much a political issue, but it should not be a partisan issue, which was, you had actually two questions in your question. One of them is about the partisan realities about how people deal with climate change, but the other is the political issues about jobs, about security, and so forth. We tried very hard to point out the fact that a lot of these issues of bias and risk need to be discussed cleanly and carefully because they are in fact politically charged. My suggestion for you in your day job, we need to show what good looks like early. The ability, for example, to identify real potential extreme weather events and prepare for them. The ability to improve grid performance. I think you want to show a couple of wins early as a way to avoid those kinds of challenges.
Thanks. Other thoughts? Ho-sung.
Yes, thank you very much.
Do we have a microphone for Professor Lee?
Thank you. Good to see you all. And it's a tremendous session, and very informative. And give us a lot of insight into this AI. I first congratulate the release of this report, and I was very much, first of all, impressed by the cover design of this report. And just question is did AI design this cover?
Great question.
Or human?
No, a person actually designed this, and we will pass along that compliment. We had a number of different iterations with her and the team coming up with the idea, so thank you. This was a great question. It was actually a human-generated design. Humans are still good for something.
Yeah. All right, thank you. Right. As I heard the presentations and in this report from chapter 1 through chapter 3, it's all about climate change, and it's much in the report. I thought if you replace the word AI with IPCC, then much of that report from chapter 1 and through reads very well. In other words, IPCC will be in great danger due to this appearance of AI, especially for the climate science aspects. And Julio mentioned about the attribution and detection. That's in fact the core activities of the Working Group 1 task. Anyway, so that's a compliment as well as the new task for the IPCC for its future, I believe, identity. Now, I think I'm just wondering how this AI can improve, our desire to have more circularity in our activities in the economy, because circularity, we need to have this improved, and hopefully close to 100% circularity, then all of the problems will be resolved. But I hope that there must be some way this new knowledge AI can help circularity problems. And more immediate is there was a mentioning of the life cycle assessment, the embedded emissions. And if we have a better information with regard to this life cycle carbon footprint of materials or other activities, then I believe people will be able to make a much more informed decisions, individual levels as well as corporate levels. So I hope many of you probably have some thought about this one already. And the last one is the IPCC in the last report emphasized very much about the importance of recognizing and also respecting the indigenous knowledge, indigenous people, and can AI be contributive to this increased awareness of the indigenous people's knowledge contribution to solving the global, these climate change problems?
There's so much there. So Ho-Sung has asked about circularity and the role there, and life cycle greenhouse gas emissions, and then indigenous knowledge. I'm just going to start on the last question, Ho-Sung, about indigenous knowledge, and turn it to see whether any of my colleagues have thoughts on the other two topics. I think one of the most exciting applications of AI involves language interpretation, and I do a lot of work in China. And I can today take a 100-page Mandarin language document and just upload it into Google Translate, and it instantly generates an English language document. And then when I give it to a native Mandarin speaker, the Mandarin speaker reads it and says, "Yep, that's it." And I ask, does it require correction? Could you please mark up anything it got wrong? And basically, Mandarin speakers say, no, this is perfect. It's good. That capability was not there 5 or 10 years ago. 10 years ago, I used to hire graduate students to do that type of work. Now this type of thing happens automatically. I think that type of language interpretation facility, which we're generating through large language models and transformer tools, it's going to be very important for indigenous knowledge. It's going to, because a lot of indigenous communities don't have the English language facilities or the other language facilities, and communication between cultures is enormously facilitated. And so I think both in terms of capacity building within countries where there may not be English language facility, but also getting knowledge from indigenous communities. I think these types of interpretation tools are going to be very important. There may be other ways too, but I think that's a lot of potential. I see Colin and Julio raising their hand. Colin.
Regarding life cycle emissions, the point there is that AI is going to help us do better at identifying novel materials with specific properties. That might be a solar material with a higher conversion efficiency, or it might be a magnet with a higher flux density. However, those models don't tend to look at the emissions that would come from manufacturing those materials, which would have to be rolled into the full life cycle of the performance of a system based on those novel materials. So I think what we're calling for is more attention to that aspect, in addition to identifying materials with specifically optimized properties for certain decarbonization uses.
And I see Julio's hand is up.
Yes. First on the indigenous peoples, an important opportunity for AI is using indigenous knowledge to limit biases. A lot of these models have biases that are built in by Western operators. They don't necessarily understand or respect the capabilities or knowledge that indigenous peoples have. Bringing those data and capabilities into objective function construction or into data sets could be a huge opportunity. With respect to life cycle, one of the places we have already seen AI provide a huge opportunity is on the footprinting. It's not quite the same thing as a life cycle, but you can get a really accurate footprint of a lot of things pretty quickly. I work at a company that does this. We were surprised at something that would take one of our guys 3 weeks to do. The AI can sometimes do accurately and well within 3 or 10 seconds. So, and one of the things that this comes back to is actually you need to train the operator. That only happens if a skilled operator can write the prompt well. And so we got to get up the literacy in order for those outcomes to matter, and that's a broad constructive training exercise. With respect to circularity, I don't think, we've built the objective functions to push that envelope yet. We haven't tried to figure out, for example, how we could do a better job sorting plastics using AI. That's something which we can probably do. It's early days. But again, fundamentally, AI is not about moving molecules around. We might be able to identify a couple of new plays or a couple of new ideas, but actually putting the technology in place, putting the hardware in place, spending the money, that's still going to end up being a separate enterprise.
I think we may have time for one or two more questions. Changhua, so we have too many questions. More questions we don't have time for, but okay. Changhua, take it away.
Okay, thank you. Just quickly, a couple of points, actually. So it just reminded me back in 2007, 2008, there was a sort of, sort of Smart 2020 project back then. There was a lot of discussion around ICT, the sector emissions and the application of ICT technologies actually in energy efficiency, whatever, stuff like that. So some of the findings you ended actually in terms of, recommendations there, that's pretty much, sort of echoing in my ear. So yeah, that was very familiar. I think back then there was roughly, if I remember correctly, so ICT sector itself emissions back then, 2007-8, was about 2 or 3% of globally. But the forecasting definitely, because the faster growth in emerging economies in particular, would definitely shoot up very quickly. But the applications of ICT technologies will bring much, much bigger sort of reduction benefits, like 15, 20% actually, in terms of improving energy efficiency, whatever, stuff like that. So that's a sort of very similar sort of a narrative mindset actually coming back, and now this round is AI. So that's a sort of comment. Couple of questions, actually. You and I started to sort of chat on the site yesterday in particular. One, this value chain perspective, right? And so, beyond whatever the focus of the work today, if you could somehow even pull further the value chain perspective, there's a lot of data generated on, constantly on real life, basically. And many of us are sort of already in it in a way, but at a very limited level of sophistication, not really getting to the AI level. Everyone looking forward, actually, some sort of tools, products, instruments that we that could be developed by you guys and many others, and that could be applied relatively easily for professionals like us in the sector, so that we'll be able to really enhance the capability in terms of monitoring footprints, recommending measures, specific actions to really reduce emissions there. Mitigation, I think that's probably is the direction to go. The other thing, actually, particularly around the monitoring, you probably noticed that Al Gore has been supporting this carbon tracing, this platform. So from China, there's another group of scientists, actually, they've been doing this carbon monitoring platform. So from monitoring capability in terms of GHG emissions, we are pretty much real life there already, or almost nearly real life already. So the question to you and the team, basically, with that capability there already, do you think it's still a lot of work to do, or it's there already that could be sort of pulled into this piece of work actually to really get the ball rolling? Thank you.
Thank you so much, Xiangwei. So we are actually over time, but Colin has got a lot of expertise on the topic you were just talking about. So Colin, why don't you close us out with a comment on that?
Very briefly to that. So I work directly I am part of the Climate Trace Consortium on my research, and indeed there's been some wonderful advances in the last few years. There's far more we can do, higher spatial resolution, higher time resolution. There's more opportunity there to bring in other remote sensing. Carbon Monitor is also an excellent tool. Indeed leverages a lot of existing data streams and is able to provide a good emissions estimate on a very high time resolution. They're complementary tools, but both of them have more ability that they can gain through further application of AI and more insights that they can offer for real decarbonization pathways.
So please take a look at the roadmap. It's going to be up on the ICEF website. Send us comments at ICEF2023roadmap@gmail.com, ICEF2023roadmap@gmail.com. Huge thanks to my colleagues. Huge thanks to everyone who supported this roadmap. Have a great day.